Welcome everyone. This is another piece of the lecture on model reference adaptive control. In this piece of the lecture, we are going to talk about a design based on state space models. However, the design steps that are shown here are actually general. They are used for different types of designs based on the Lyapunov approach. The first step actually is to find a structure for the controller, then drive the error model, and then propose a Lyapunov candidate function. We take the time derivative of that function, and accordingly we'll have some negative terms. We'll leave those terms, but there will be also some terms that we can determine their signs, and these are set to 0, so we will produce the adaptation equations. Now let's consider a state space model in the usual form: x dot equals ax plus bu, y equals c transpose x. I'm going to assume that x belongs to a space of dimension n, while y and u belongs to a space of dimension 1. That means that I'm considering a single input, single output system. Okay. Also, for simplicity of the derivations, I'm going to assume that the system is third order. However, this is not a restriction. What we are going to do is apply to any order n. Okay. If we assume the system in the controllable form, that means we will have here an identity matrix of dimension n minus 1. In that case, it would be a 2 by 2 matrix. I will have here a vector of zeros, and down here we will have the coefficients of the characteristic equation of the corresponding system. This is the B vector, and this is the C vector. Now, the form that we are going to propose for the controller would be a feed-forward term from the reference plus a feedback term from the states. We can write this as theta transpose omega, where theta will consist of the gains k node, k1, k2, and k3, while omega would be the reference x1, x2, and x3. These are the components of the state vector. Okay. Now, as I said, the second step is to derive the error equation. Now, before we derive the error equation, we have to find an expression for the closed loop system. We have x dot equals ax plus bu, so I'm going to substitute here for u by its expression, so that will be ax plus b times theta transpose omega, and that also can be written as ax plus b times k node r plus k transpose x. I will combine terms that include the state vector together, so that will give me a plus b k transpose times x plus b k node r. I'm going to call a plus b k transpose a subscript c, c for closed loop, x plus b k node r. So this is the closed loop equation of the model, and the matrix A plus B k transpose will have eigenvalues that would correspond to the closed loop poles of the system. Now, to calculate an expression for the closed loop state matrix AC, we substitute A from the modeling equation of the system, and then we add the vector b times k transpose, and the result, as you can see, would be a system still in the controllable form. I have here still the identity matrix of dimension n-1, which is 2 in our case, and a vector of zeros. And down here I will have the coefficients of the characteristic equation as affected by the state feedback. The equation for the gain matrix, the input gain matrix BC, is B times K transpose, and here again we have the first two rows equal to zeros, and the last one would be K naught times B3. The reference model xm dot equals am xm plus bmr will take again the controllable form. This is the identity matrix, this is a vector of zeros, and here would be the coefficients of the desired characteristic equation of the system, and this is the b vector. Okay, the next step is to derive the error equation. We will define the error as the difference between the state of the actual system and the state of the reference model. In that case, E dot would be x dot minus xm dot. Now I'm going to substitute for x dot from the closed loop equation that we have derived before. So that would be ACX plus BCR minus AM XM plus BMR. Now we would like to have an equation that has the error as the state vector multiplied by the state matrix AM, because we guarantee that this state matrix is stable. So in that case I have to multiply AM by x minus xm, but then this adds a term which does not exist in the original equation, so I have to compensate for that. That's why I will add here a term AC minus AMX. So the term minus AMX would actually cancel the added term AM times x that appeared in the first line. Then I will have BC minus BM times R. So that gives me AM times E plus AC minus AM times X plus BC minus BM times R. Now I will try to find simpler expression for the last two terms in the error equation. So first let us calculate the value of AC minus AM. This is the expression for AC, and this is AM. Now if you subtract, you will find that the identity matrix that appears here will cancel the identity matrix in the AM matrix, so I will have two 0 rows in the resulting matrix here, and then the last row would be just the difference between each element and the corresponding element in AM. Similarly, I calculate BC minus BM. Now I need to multiply this matrix, which is AC minus AM, multiplied by X, and this vector multiplied by R. I'm going to call the first element here phi 2, second element phi 3, and third element phi 4, while this is phi 1. So the result of the multiplication of this matrix by x would be 0 first and second rows, and then I will have phi 2 times x1 plus phi 3 times x2 plus phi 4 times x3 plus 2 zeros here. I'll multiply this vector by r, and I'll have here phi 1 times r. I'll put that in the form a vector bi times phi transpose omega, where I defined here the different vectors. The vector bi is just a column vector with 2 zeros at the upper rows and then 1 at the last element, and phi transpose is just composed from phi 1, phi 2, phi 3, and phi 4 as shown here, and omega would be r x1, x2 up to x3. This way I can write the error equation as E dot equals AME plus B subscript I times phi transpose omega, and that would be used later within the Lyapunov function to calculate the adaptation equation. Okay, once we derive the error equation, now we can look at a candidate Lyapunov function. Typically, the Lyapunov function would be a quadratic function in E and phi. Having here a matrix P, which is positive definite, and another matrix here P gamma, which is also positive definite. Normally gamma is a diagonal matrix, and the elements of the diagonal elements will be the adaptation gains, as we are going to see later. So in order to force this function v to be a Lyapunov function, we have to show that v dot is negative definite or negative semi-definite. So I'm going to take the derivatives of the different terms in v. So I would get E transpose P times E dot plus E dot transpose P E plus phi transpose gamma to the minus 1 phi dot plus phi dot transpose gamma to the minus 1 phi. Now the expression for E dot here and here would be taken from the error equation that we have derived before. So if I substitute for that, I would get E transpose P times AME plus BI phi transpose omega. This is for the first term. For the second term, I will get AME plus BI phi transpose omega all transposed times P E. And I notice here that these two terms actually are similar, since they are actually scalars, and the transpose of a scalar is the same scalar. So phi transpose gamma minus 1 times phi dot is equal to the transpose of the second term. So I can write then the summation as 2 phi transpose gamma to the minus 1 phi dot. Now I will collect terms that include E together. So from the first term here, I would get E transpose times P AM and then multiplied by E. And from this term here, in the second line, I would get AM transpose, because this whole bracket is transposed, AM transposed times P times E. So now I'm finished with that term, and then I will have E transpose P times BI phi transpose omega and from the second term here within the bracket I would get, notice that phi transpose times omega is a scalar. This is a row vector times a column vector. So I will take that vector outside. So like phi transpose omega like this. And then I take the transpose of pi. So it's pi transpose times p times e. And then 2 phi transpose gamma to the minus 1 phi dot. Now again, if you look at these two terms, you will notice that the product E transpose P times Bi is a scalar, phi transpose omega is a scalar. Now the same thing here, this is a scalar and this is another scalar. So these two scalars here are equal. So if I take the transpose of the second, I will produce the first, and then they will be similar. So I can say that the summation of the two terms here will be just twice one of them. So I'm going to write then the error, the V dot equation as E transpose times minus Q times E plus twice E transpose P Bi phi transpose omega plus 2 phi transpose gamma to the minus 1 phi dot. Now here I made the substitution P AM plus AM transpose P equals minus Q, and this is correct since AM is a stable matrix. It has stable eigenvalues, so the Lyapunov equation is fulfilled, and I can replace that sum by minus Q, where Q is some positive definite matrix. Okay, now if we look at the last equation here, this is a negative term, but these two terms actually are indefinite. We can't tell their sign, so that's why we force them to be equal to 0, and that would produce minus E transpose times Q times E. So this is a negative semi-definite Lyapunov function, and if we put these two terms equal to 0, you would get E transpose P times B omega plus gamma to the minus 1 phi dot equal to 0, and that will result in phi dot equals minus gamma E transpose P times B omega. So this is the adaptation equation. As I mentioned, gamma would be a diagonal matrix with the diagonal elements gamma 1, gamma 2, and so on. So this will be the adaptation gains that we talked about later on. Again, this is a scalar, and omega would be a vector that's composed of R x1, x2, and x3. Now let's look at the derivative of phi. This is the definition of phi as we have mentioned before, and I'm assuming here, of course, that the parameters of the reference model to be constants, and we are assuming that the parameters of the plant, the unknown parameters, to be constants or varying very slowly with respect to the adaptive system. So when I take the derivative of phi, I would assume them as constants. So the result of the differentiation would be B3 K node dot B3 K1 dot B3 K2 dot, and finally B3 K3 dot. So this is the result of phi dot transpose. I can take, of course, B3 as a common factor, and the result would be just theta dot, where theta dot would be k naught dot, k1 dot, k2 dot, and k3 dot. This is the vector. And consequently, I can write the adaptation equation instead of having phi dot in the left hand side of the equation. I would just have theta dot, but then I have to divide gamma by b3, and the division would result another vector, another matrix gamma bar, where the diagonal elements of that matrix will be divided by b3. I don't have to know b3 because this is again the adaptation gain. I just have to know that b3 is positive or negative, whatever the sign. I mean, the sign has to be known in order to write the adaptation equations. Okay. Now, since v dot is negative semi-definite, we can use again Barber's lemma to show that v is bounded below, v dot is negative semi-definite, so v double dot is bounded. Same arguments that we have used before, and that will lead to the conclusion that v dot will go to 0, and if v dot goes to 0, then e has to go to 0, and that consequently will mean that x will go to the required trajectory xm. We did the analysis, the previous analysis, assuming a third order system, but as I mentioned at the beginning, this is valid for any order n. However, there are some assumptions. The first assumption is that we assume that all states are measured. So this is a state feedback control design. The second assumption that we have made further is that the system is in the linear form, and it can be put in the controllable form. So the derivation is based on the controllable form of the system representation. Now, how to implement the algorithm? We have now the adaptation equation. So what we do is that we measure the state vector x. We know r, or we measure r, the set point, and we can also measure the states of the reference model. So from that, we form omega, which consists of the set point and the state vector. We calculate the error, which is the difference between x and the reference model state variable xm. And then we calculate theta by integrating the adaptation equation. Once we get theta, we calculate the control signal u, which is theta transpose times omega, and we are done. So this is completes actually the design of a model reference adaptive controller using state feedback. Okay, thank you.